Billions of liters of water must be pulled from the Pacific Ocean to save the interior. California faces one of its most persistent and devastating enemies on the West Coast. Rivers have run dry, leaving only scorched beds behind. Fertile farmland has cracked into red dust under the relentless sun. One can notice how the landscape has withered. But this is just the beginning. Why resort to such extreme engineering measures? A bold idea emerged to reverse the damage. At first glance, the situation seems hopeless. But in reality, technology offers a path forward. Massive desalination plants are being built to treat the intake. Advanced wastewater recycling technology works alongside the fresh supply. Water pipelines stretching for hundreds of kilometers cut through the terrain. The goal is to bring a once-dead land back to life. And this is not the limit. These technologies quietly power the solution to the greatest water crisis in history, $3.5 trillion United States dollars. This colossal figure represents an economy that would rank as the world's 5th largest if California were a sovereign country. Why does this agricultural and financial giant face a desperate struggle for basic survival resources? It seems paradoxical given the state's massive wealth. The answer lies in the intense demands of the agricultural sector, which produces 1/3 of the United States' vegetables and 2/3 of its fruits and nuts, yet consumes nearly 80% of all human-used water in the region. One can notice how miles of lush crops thrive in valleys that would otherwise be arid. But this is just the beginning of the imbalance. The irony remains that California can hardly supply its own water naturally due to its difficult geography. The state sits clamped between the cold waters of the Pacific Ocean and the towering Sierra Nevada range, which acts as a natural wall, blocking much of the incoming oceanic moisture. Most rainfall lands exclusively in the north, while the south endures an unrelenting semi-desert climate. Over 60% of the natural water supply comes from Sierra Nevada snowmelt, a massive water bank that forms on the peaks each winter. It gradually melts to feed rivers and reservoirs through the heat of summer. However, that cycle is collapsing. Snowpack volume has dropped by 20 to 60% in drought years and melts weeks earlier than historic norms. Consequently, California is trapped in its worst drought in 1,200 years, with major reservoirs like Shasta, Oroville, and Meade falling to just 40% of their total capacity. It is visible how the shorelines have retreated, exposing vast stretches of dry earth. That is why Americans could not just sit back and wait for mountain water. Instead, they turned to a nearly endless source, seawater. It gets more complex further on. Because seawater contains about 3.5% salt, it is far too saline to drink or use for irrigation. That is why desalination technology emerged, providing a virtually limitless supply of usable water, necessitating giant desalination plants built along the Pacific coast. At first glance, pumping water seems simple, but in reality, the separation process consumes immense power. Every day, this plant converts 7 million liters of seawater into drinking water using significant energy in just 90 minutes. The fresh water flows calmly into the supply network, ready for the next stage of distribution. 15 million liters per day is the massive volume drawn by a single pipe, measuring just 63 centimeters in diameter. To handle this throughput, engineers install intake pipelines made from robust carbon steel or high-density polyethylene, often measuring 2 to 3 meters across. These structures are built to withstand salt corrosion, crushing water pressure, and the relentless impact of ocean waves. Each section stretches for dozens of meters and is lowered into place using heavy lift cranes, where it is connected piece by piece with high-pressure gaskets and fully sealed welds. But this is just the beginning of the infrastructure setup. The entire pipeline system is rigidly secured with steel frames and seabed anchors to maintain stability against strong currents in the harsh coastal environment. Why do engineers extend these pipelines a few hundred meters offshore instead of drawing water directly from the coastline? Building the intake near the beach would reduce construction costs and technical complexity. This distance is critical because barriers and intake filters located far offshore catch large floating debris and prevent marine life from entering the flow. Powerful pumps push the seawater toward the plant at a rate exceeding 10,000 liters per minute. As the water enters the system, biological intruders like jellyfish, crabs, and small fish encounter a massive screen designed to block anything larger than 4.5 millimeters in diameter. One can notice how the mesh physically stops these organisms while allowing the liquid to pass. After this initial barrier, the water flows through finer screens to remove the remaining large particles. However, the fluid is still far from the necessary purity. Suspended sediment remains in the flow, requiring a process called filtration in specialized gravity tanks. Water flows downward through layers of sand, where the gaps between grains are so small that only liquid can pass while particles get trapped. The sand continuously moves in the opposite direction of the water flow, causing dirty particles to cling to the surface of the grains. Anything larger than roughly 1/10 the thickness of a human hair is removed at this stage. Large paddles stir the water as the plant adds sodium hypochlorite as a disinfectant and ferric chloride as a coagulant. It gets more complex further on. The coagulant causes fine sand and waste particles to clump together into larger flocks, which then settle at the bottom of the tank. Most of the dirt is removed, but the water is not yet clear enough for the desalination stage. The fluid enters the cartridge filtration system, which acts as the final line of defense before reverse osmosis. Inside each housing, multiple cartridges made of tightly compressed fiber layers feature pore sizes as small as 1 to 5 microns. As water flows from the outside toward the center of each cartridge, microscopic particles get trapped between the fiber layers while clean water passes through the cartridge wall. Engineers monitor the system and replace saturated cartridges to ensure maximum efficiency. Transition to the next level. The seawater moves to the most critical stage of the facility, separating the salt from the water molecules. At first glance, reverse osmosis seems like a simple filtration process, but in reality, breaking the electrostatic bond between salt ions and water molecules requires immense mechanical force. High-powered centrifugal pumps generate pressure significantly greater than natural osmotic pressure to drive the process. Each component of the pumping system controls a specific stage, gradually increasing compression as the water moves through successive phases. By the time it exits the final stage, the pressure reaches about 60 bar, which is roughly 60 times atmospheric pressure. And this is not the limit. One can notice how the water exits the first round almost salt-free, yet it still contains trace ions and microminerals. A second reverse osmosis stage forces the liquid through even finer membranes under lower pressure to achieve higher salt removal efficiency. This step reduces electrical conductivity to extremely low levels, stripping out the remaining ions and bringing the water to true purified quality. The resulting stream is ultra clean, but needs chemical balancing before humans can safely drink it. The plant adjusts the pH by adding a small amount of acid or a balancing solution to bring the liquid back into a safe range. Since the water now lacks essential minerals, elements like calcium and magnesium are introduced during the remineralization process. This restores the mineral profile, increases alkalinity, and improves the taste, making the water healthier for consumption. Everything only gets more complicated when considering the economics. High-pressure pipelines carry the clean water to massive storage tanks within the plant, where it awaits distribution. Pumps send the liquid into the municipal supply network or deliver it to drought-stricken agricultural regions for irrigation. Although this technology is advanced, desalinated water remains relatively expensive, often costing 2 to 4 times more than conventional water, depending on the location. The process concludes at this phase, leaving the processed water ready for practical use. "700 kilometers of artificial waterways cut through the landscape, reshaping the destiny of an otherwise dry region." Why does California rely on such a complex network instead of simple wells? The state faces a constant battle against aridity that local sources cannot solve alone. Without this engineered intervention, the fertile valleys would return to dust. It all begins in the Sierra Nevada, where winter snow piles up meters deep. When summer arrives, the melting snow produces a precious flow of fresh water that would otherwise rush out to sea. Engineers block this path with massive dams like Shasta, Oroville, and Folsom, creating a reservoir system with a combined capacity of tens of billions of cubic meters. These water banks protect California through every drought cycle. But this is just the beginning. From these reservoirs, the water travels south through the Central Valley Project and the State Water Project. One can notice how the California Aqueduct acts as the system's backbone, stretching nearly 700 kilometers across valleys and deserts. In places where the terrain rises sharply, giant pumping stations push the water upward against gravity. It is visible how the liquid mass climbs more than 600 meters up the Tehachapi Mountains to cross the range. The process is only gaining momentum. At first glance, the water flows effortlessly through the channels. But in reality, delivering each cubic meter comes at a steep financial cost. The fluid is distributed through a vast network of reinforced concrete pipelines and branching canals, reaching every city, farm, and industrial zone. This requires tens of billions of dollars in initial construction investment, plus billions more each year for electricity and maintenance. Consequently, many areas have had to raise prices for both household and agricultural consumers just to keep the system operational, and this is not the limit. This very same water highway is now opening up a new future, combining flow from the mountains with water from the sea. Because the existing infrastructure can seamlessly connect to coastal desalination plants, California can blend multiple water sources within the same network. This transformation turns the system into the beating heart of 21st century water security. Thanks to this vast system of dams, reservoirs, and aqueducts, millions of hectares of farmland in the Central Valley now possess a stable year-round source of irrigation water. The region supplies more than 1/3 of America's vegetables and 2/3 of its fruits. Fields that once depended entirely on unpredictable snowmelt can now maintain production even during severe droughts. Crop yields have increased dramatically, helping turn California into one of the most important agricultural hubs in the world. Despite the high cost, this system remains the foundation for survival in an arid climate. The water continues its journey through the canals, ensuring the life of the region proceeds without interruption. Not a single drop is allowed to go to waste in the arid climate where California strives to thrive. Why are massive wastewater recycling plants constructed alongside seawater and natural freshwater sources? It would seem that existing natural supplies might suffice for a time, but these facilities are essential to both supply additional clean water for agriculture and cities and to reduce pollution entering rivers, lakes, and the ocean. The journey of water treatment begins deep beneath the city within a vast network of underground sewers. One can notice how every drop from toilets, sinks, and industrial facilities converges here, creating an immense flow that arrives at the treatment plant, carrying an unpredictable mix. Shredded paper, plastic bags, wooden branches, sand, gravel, and even grease swirl in the current. To prevent the entire system from clogging, the process starts with a row of stainless steel bar screens standing tall like the first gatekeepers. These mechanical grids trap large debris, from rigid plastics to scraps of fabric, ensuring that the flow downstream remains unobstructed. But this is just the beginning. In the primary treatment stage, the wastewater that has already passed through bar screens and grit chambers is directed into enormous settling tanks. These structures, often circular or rectangular, can hold thousands of cubic meters of water and function as temporary basins. The velocity of the flow decreases dramatically in these reservoirs. Heavier organic particles, such as fecal matter, food residues, and shredded paper, begin to sink to the bottom to form a dense layer known as primary sludge. At first glance, this separation seems like a simple pause in movement, but in reality, it is a critical stratification phase. One can notice how mechanical skimmers move continuously in a circular motion on the surface. The equipment gradually collects floating grease and debris to leave behind a clearer middle layer of water. Through this simple but powerful mechanism, the sedimentation tank serves as the first line of defense. It does not end at this stage. Once the water has passed through the primary sedimentation stage, it enters the decisive phase of biological treatment inside the aeration tanks. These are massive concrete basins, several meters deep, equipped with thousands of fine air diffusers at the bottom. Tiny bubbles rise continuously, stirring the entire water column and delivering a steady supply of oxygen. Within this oxygen-rich environment, billions of aerobic microorganisms come to life, consuming and breaking down the remaining organic compounds. In truth, these microorganisms are the invisible tiny workers tirelessly cleaning the water day and night. The process is only gaining momentum. As oxygen fills the tanks, the activated sludge begins to form clusters known as flocks, binding countless microscopic particles that remain suspended in the water. The water leaving the secondary settling tanks appears much clearer, yet within it remain countless microscopic particles and microorganisms far too small for the human eye to detect. Therefore, to remove them, the flow is directed into massive filtration chambers, where layers of dark membranes are arranged in sequence. This is the microfiltration system functioning like an ultrafine gateway that blocks bacteria, parasites, and the tiniest suspended solids. The purified stream is pumped under tremendous pressure into rows of white cylindrical tubes known as the reverse osmosis modules, the very heart of the entire system. Inside each tube, multiple layers of semi-permeable membranes are tightly wound with pores hundreds of times smaller than the width of a human hair. Here, every molecule larger than H2O is stopped in its tracks. The pressure inside the system can reach tens of bars, driving a process that is both powerful and exquisitely precise. By the time the water exits these white cylinders, it has achieved an extraordinary level of purity. One can see the fluid shimmering like liquid crystal. This is the decisive transformation point, where cutting-edge technology turns wastewater into water that is clean enough to drink. "100% purity is the standard for water prepared to drink. One can notice the crystal clarity as the liquid exits the facility. This defines California's bold mission to reclaim every drop of water for the future. The technical cycle continues without pausing." Why rely on such engineering marvels? It seems traditional sources should suffice, but verified data confirms that these technologies reshaping our world are the only path to stability. At first glance, the flow seems natural, but in reality, it is a product of complex calculation. the equipment gradually stabilizes the output pressure. It is visible how the water fills the tanks. The resource is now ready for safe consumption.